Hello, my name is Leonid Karlinsky. I'm a senior research scientist in MIT IBM Lab of IBM Research. Today, I'm happy to present you some of our recent work in the space of learning with limited supervision. So why would we need less supervision? The why is really trivial. Collecting and annotating data is always a pain. It is hard, there are many privacy issues, and it costs. But how can we do less of this? Well, there are actually many options. We can collect less annotations or less data in few-shot or semi-supervised settings, or even only data without annotations in self-supervised setting. We can go with cheaper, lower quality labels by allowing synthetic data or noisy annotations. And finally, we can ask for lower complexity annotations, which is easier to collect by using, for example, the weakly supervised setting. Having realized that for quite some time now, we are strongly investing in reducing our dependence on manual supervision, as well as on availability of real data in general. You can find a lot of interesting IBM-affiliated research work, not only on the so popular these days few-shot or self-supervised learning directions, but also on learning from synthetic data, and even on pre-training using fractals and noise. Needless to say, this also resolves a lot of data privacy and copyright issues that are inherent even to ImageNet. Here are some examples of IBM research projects involving data synthesis, which is a cool way to avoid a lot of data and labeling dependence while preserving privacy and copyright. And of course, we have a lot more to offer in the few-shot learning and learning with less label space. You are more than welcome to have a look on these and other works. Today, we are going to focus on several works targeting reducing sample quantity and labeling complexity. As I mentioned, we also have some interesting work on learning from synthetic data. But those would be beyond the scope of this talk. If you are interested, you are welcome to contact me or simply find those on archive. Let's first cover some works on self-supervised and cross-domain self-supervised learning. In this part, we would briefly highlight two works appearing on this year's CVPR and ECCV respectively. In the bread work on the left, we will show an effective way of learning a self-supervised representation that semantically aligns multiple domains and even generalizes to unseen domains without using any labels. In self-classifier work that would be presented on Tuesday morning post-session number 1, we show a simple and elegant method for state-of-the-art unsupervised classification using uniform priors. We will start with unsupervised domain generalization by learning a bridge across domains, or BRED for short. That was a result of fruitful collaboration between IBM Research, MIT, Boston, and Tel Aviv universities, and was presented as an oral on this year's CVPR in New Orleans. Our goal is to learn domain-invariant class-aligned representations without any labels, applying self-supervised learning to data from multiple domains. However, without special handling, self-supervised training tends to separate domains before separating classes, thus failing to achieve our goal. Our solution is to let our model invent an intermediate auxiliary domain serving as a bridge for semantic alignment. By aligning all domains to this bridge, we consequently align them to each other. Let us first review the common tasks in the cross-domain literature. All these tasks aim at reducing the amounts of supervision needed for the new target domains. In domain generalization, we train on labeled source domains and test generalization to unseen target domains. In unsupervised domain adaptation, we train on labeled source and unlabeled target domains, testing performance on the target domains using their held-out labels. In our work, we take a step further to reducing required supervision. we consider 3 tasks of completely unsupervised cross-domain alignment. Unsupervised domain generalization extends domain generalization by having also the source domains as unlabeled during training. Similarly, fully unsupervised domain adaptation extends UDA, removing source domain supervision, making the roles of source and target completely symmetric at train time. We also propose a third, even more challenging setting of generalizing between cross-domain benchmarks, training our model on one benchmark and testing it on other benchmarks, including different domains and different classes. Our approach extends MOCO by He et al. One of the views in our positive views pairs is transformed by a learned image-to-image breadth domain mapping psi. This psi is edge map regularized to reflect our intuition that edge-like transformations naturally make arbitrary image domains more similar. The positive views are contrasted with negative views only from the same domain, thus preventing them from pushing the other domains apart in the embedding space. For improving domain invariance of the embedding, our approach also features a domain discriminator and the corresponding adversarial loss. Detailed description of the model and all the losses can be found in our paper. In our experiments, we evaluated Brad on all the 3 completely self-supervised cross-domain alignment tasks we have discussed in previous slides. Here we show significant, up to 17% absolute improvement in unsupervised domain generalization benchmarks proposed by DIUL paper by Zhang et al. We attain up to 15% absolute improvement in fully unsupervised domain adaptation on DomainNet, comparing to all few-shot UDA baselines from PCS paper by Yu et al. Importantly, as opposed to other methods, we do not use any labeled samples during training. Finally, we observe up to 7% improvements in generalizing from DomainNet to Office Home, PAX, and WISDA without any additional training on target benchmarks, using just 1 or 3-shot KNN for evaluation. We compare to all the leading self-supervised learning baselines, highlighting the benefits of contrastive learning modifications proposed in our approach. We provide a detailed ablation study evaluating the merit of different architectural components, as well as model initializations and training setup. Looking at qualitative examples of image transformations induced by Brad, we can clearly see how it reduces domain differences while preserving the discriminative semantic content of texture and shape. We also provide a demo of using Brad for cross-domain retrieval on the entire DomainNet test data without any cherry-picking. The paper, the code, and the demo are all available online. We hope that this work will serve as an inspiration for further research into exciting and very practical topic of completely unsupervised cross-domain alignment. Next, let's discuss the self-supervised classification network, which is a cool self-supervised learning work we co-authored with 2 fantastic researchers, Elad Amrani from IBM Research Labs and Professor Alex Bronstein from the Technion. In this work, we show self-supervised class learning could be realized as a simple training of a classifier that would make a consistent prediction for 2 or more views of the same image, coupled with a uniform prior that prevents degenerate solutions. In the paper, we also show that using a few simple Bayesian tricks, this method can be elegantly realized with a few lines of code on top of a standard classifier training pipeline. Equipped with this method, we were able to show state-of-the-art results in self-supervised classification, that is, unsupervised discovery of classes without any further fine-tuning. We showed it on ImageNet and its multiple subdivision hierarchies, while beating all self-supervised representation learning and self-supervised classification methods. For more details, you are more than welcome to visit us on the morning poster session on Tuesday, October the 25th. Let's now switch gears and talk about coarse-to-fine few-shot and other weakly supervised learning works. We'll mainly discuss two of our papers from last year's CVPR and ICCV concerning with a different form of weak supervision, be it a coarse classes only supervision for subsequent fine-grained classes, future specialization in the anchor paper on the left, or learning to localize free-form textual queries without any location supervision in our detector-free weakly supervised grounding work on the right. I will also briefly mention another cool work on weakly supervised few-shot object detection in the end of the talk. We'll start with fine-grained angular contrastive learning with coarse labels work, also known as anchor. It was presented as an oral on last year's CVPR and as a fruitful collaboration with Tel Aviv and Boston University researchers. Let's look on the traditional few-shot learning setup. We have few examples for some classes in a few-shot episode and need to classify a given query. Typically, in both training and testing, the classes are random and hence, with high probability, coarsely different from one another. In this work, we like to consider a very different yet very practical setup, where during training we can only generate episodes from coarsely labeled classes, such as different animal types and so on, while when our model is tested on novel classes, these can be either fine-grained subclasses of training classes or completely unseen, yet fine-grained subclasses of other classes. Our method involves an interesting combination of supervised inter-course class learning with given course labels and self-supervised intra-class learning to well separate the fine-grained subclasses of each course class. And we have our proposed angular normalization component, or NCOR for short, that induces synergy between the supervised and self-supervised learning objectives. In gruesome detail, our method includes a supervised course classifier branch, self-supervised contrastive branch with a negative skew per class, and not a single negative skew as in the original MOCO. The angular normalization component that normalizes the contrastive loss to operate in the space of angles around each class representative vector. This vector is actually the class weight of the course classifier for that class. And finally, we have the supervised cross entropy and self-supervised info in C losses to govern the optimization. In terms of results, Anchor does pretty good, showing excellent gains of up to 9% over many baselines on breeds, which is the recently proposed ImageNet-based dataset with clearly defined coarse and fine levels hierarchy. Moreover, we outperform models trained with more data, such as full ImageNet trained MOCO or SWAV. We outperform ensembles of strong models. And we also show how Anchor can be generalized to subclasses of classes unseen during training and still show strong gains there. We have many additional experiments and ablation studies in our paper, and we will not discuss them here for lack of time. Here, I will only note that in these studies we saw an interesting tendency of Anchor to enjoy longer training, and where supervised baselines tend to overfit or stagnate with more epochs, Anchor actually continues to improve and increase its gains, reaching up to 28% improvement after 800 epochs. Qualitatively, Anchor produces a well-structured feature space and appealing last layer activations, highlighting the objects nicely despite being trained using only weak coarse classes image level supervision. Next, let us have a look on our recently presented oral paper at ICCV, which is detector-free weakly supervised grounding by separation. This work was led in IBM, but as you can see, also involved a great collaboration with many famous research labs. In this work, our task is visual phrase grounding, where we aim to locate specific free text query phrases within an image. For example, in the image on the left for a brown squirrel query, we would like the squirrel to be highlighted. And for the query a snowy area, we would like to highlight the snow below the squirrel. And here we show the results of our method for this image and these queries. Notice that this is different from object detection, as the queries are free text and the object classes are not predefined in advance. First, let's see some highlights. Our method is weakly supervised, meaning it is only trained using loosely paired text and image pairs without any location supervision. We show significant, up to 10% performance gains over state-of-the-art in this setup. While most recent grounding methods rely on existing pre-trained object detector intuitively violating the weak supervision assumption, being weakly supervised has clear advantages for free text queries non-overlapping the detector vocabulary. You can see some examples on the bottom right. Building on this, we show our method can be complementary to detector-based approaches, attaining up to 9% accuracy gains over global grounding state-of-the-art when combined with detector-based methods. Our grounding models comprise of three main building blocks. The encoder extracts the image features at multiple levels. The query phrases are also encoded by a language model and attenuate the visual features produced by the encoder. Finally, the attenuated features are passed to the decoder, which creates a heat map predicting the location of each query phrase in the image. To train this model in the weakly supervised setting, we need to create some training signal which will force the network to highlight the relevant image regions based on the textual query. Each image can be seen as a blending of multiple images, each depicting a certain semantic part. For example, we have the image of the park in the background, and the images of the dog and the boy and the frisbee in the foreground, all blended together to create the full image. Our simple intuition is that in the weakly supervised setting, we can substitute the naturally blended images with random blending of random image pairs, and this in turn can be effectively used to train a grounding model. And this is how we do it. During training, we randomly select pairs of images with their corresponding captions. We then generate a random blending alpha map for each pair. This alpha map is used to mix the two images to create a blended image, which will be our input to the model during training. Notice that by construction, each pixel of the blended image has a known association to one of the original captions. We show how this simple and yet effective method can be used for training strong grounding models. During training, we employ the encoder, conditioning, and the decoder construction as I explained earlier. We apply it to these synthetic blended images and ask the model to produce alpha or 1-alpha maps depending on the conditioning. Due to lack of time, I will not bore you with the gory details right now, but please look for them in our paper. I will only highlight that the conditioning and decoding is performed on multiple levels of the UNet responsible for producing the final output, and that there are some additional regularization losses at play that help the training to succeed to generalize to natural non-blended images at test time. Here you can see our method in action. The output for the two queries, a dark-haired drummer and his set. Even though the network has only seen synthetic blended images at training time, and this is a natural image, the outputs nicely highlight the relevant parts of the image described by each query. In the paper, you can also find a lot of quantitative results, clearly highlighting the performance gains of our approach in various setups and on multiple standard grounding benchmarks. This concludes this brief overview of our weekly supervised grounding by separation work. You are more than welcome to read the paper and our code and the code is already available online. You can see the link in the bottom of the slide. So before we conclude our talk, let's see some additional nice work very briefly. This work is targeted towards weekly supervised few-shot object detection. This was published on AAA 21. And it's a great collaboration with many researchers whose pictures you see on this slide. So in this work, we show that a nice approach to weekly supervised few-shot detection. But let's first understand, why it's even needed. So to pre-train any few-shot model, one of the major required components is that we need to collect and annotate massive training data for what is called the base classes. And this, can easily become very expensive, especially if our annotation, is for detection and it needs to include, for example, bounding boxes. So since few-shot methods are notoriously bad under domain shift, we actually need to do this process of base classes annotation for any new domain where we want to enter with our few-shot detector. And this easily becomes very expensive. StarNet is the first weekly supervised few-shot object detector that can learn to detect unseen target classes without observing any bounding boxes at any stage of the training, nor in the adaptation to the few-shot classes. So no bounding boxes at all, and we are able to detect objects nonetheless. So you're welcome to check the paper for the efficient end-to-end architecture employed by StarNet and how it can support, which is basically some neural implementation of a half transform. And in the paper you can see how this can support multiple instances of the same class on the image and non-rigid objects. And here you can see some nice performance gains StarNet has obtained over a large variety of different baselines on some challenging data sets. Of course, the code is available online. And here you can see some nice video of StarNet converging on a set of test on a test episode observed during the progress of the training on the base classes. You can see how this converges basically to the correct prediction, which means that all the query set on the left selected the correct support image on the right and also localizes the objects despite those objects being small birds of different kinds. Thank you. Here is a list of links of papers we discussed today. I will be more than happy to hear your comments or answer any questions you may have.